Now we are going to apply some of the circle geometry theorems. So we have a circle with points L, K, and R on the circumference, and then we are told that in the diagram, O is the center of the circle, okay? And then the diameter LR, there it is, it suspends LKR, angle LKR. We know that's an angle because it has a head on top of K there. So angle LKR here, because it's suspended by diameter LR, then there's a theorem that tells us that an angle suspended by a diameter is equals to 90 degrees. Remember, the reason there is that suspended by diameter. So that's a theorem on its own. So L is another point on the circumference, and chords LN and KN are drawn. We are given that LN is equals to 58 degrees. Okay, so calculate, given reasons, the size of LKR. Okay, that's a given. This is as simple as saying LKR is equals to 90 degrees. What is the reason? Suspended by a diameter. Okay, then we will get our 2 marks there. And then we are also required to find the size of angle R. Okay, let's check. What do we know? We have 90, we have 58 there. Angle R is in triangle L, K, R. And then we know from previous grades that the sum of angles of a triangle equals 180. So we see that angle R plus angle L1 plus angle K or LKR, they are all equals to 180 degrees. We have to give a reason. The reason here is that sum of angles of a triangle, okay, it's known that the sum is equals to 180. So let me just move this 3 here. We know that number 3 we're going to look for N. Okay, so R is what we are looking for. L1 is given to be 58. Then K, we know that it's 90. We have proved that in question 1. This equals to 180. So that means angle R will be equals to 180 minus 90 minus 58 equals to 32 degrees. Okay, and then lastly we are required to find the magnitude of angle N, the angle here. This is the easiest one. This is equals to, okay, angle N is equals to angle R equals to 32. Why are we saying angle N and R are equal? That is because the reason will be angles on same segment. Okay, that is another theorem that we learned previously, that if two angles are suspended by the same chord, so these are suspended by chord LN or R, these two angles are suspended by chord LK or arc LK, and both of them are at the circumference. That means they are equal. So normally we recognize that by the shape bow tie, when they create a bow tie shape. So that was a theorem, remember it. Angles on the same side of the segment, in our case being angle N and angle R, they are both on the circumference of the circle, and they are both suspended by the same arc or chord LK. So that means they are equal. And the reason we can just give us angles on the same segment. Okay, that was an easy one. Alright, so we now get to prove one of the theorems, one of the 9 theorems for 6 marks. That's a lot. Okay, so we are given in the diagram, O is the center of the circle, A, B, C are points on the circumference, chords AC and BC and RD, OA and OB are drawn. Okay, we also have OC are drawn. So angle A is equals to X and angle B is equals to Y. So first we need to determine the size of O1, where's O1, here's O1 here, in terms of X. Okay, so let's look at triangle. In triangle AOC, that's AOC, that's a triangle. So first we notice that OC is equals to OA. Why? Both of them are from the center to the circumference, center to the circumference. They are radii, or we can say given. Since both of them are radii, therefore angle C1 is equals to angle A equals to X. Okay, that is our reason up there. Okay, and then O1, what will be O1 then? O1 will then be equals to angle C1 plus angle A. Okay, what is our reason in this case? It's the exterior angle, of a triangle. We know exterior angle of a triangle is equal to the sum of opposite co-interior angles. Okay, if we continue with this, O1 will then be equals to C1, we just determined that it's X, and then A1 is given that it's X. Therefore, angle O1 in terms of X is equals to X plus X, which is equals to 2X. Alright, so another thing that we have to solve is to prove that the theorem that states that the angle suspended by the arc, there's the angle there, angle O or AOB, suspended by arc AB, okay, AOB, suspended by arc AB, is equals to twice the angle suspended by the same arc at the circumference. We do have an angle at the circumference which is angle ACB. So that means it's at the circumference, it's also suspended by AB. So we need to prove that AOB is 2 times ACB. If you're going to follow the same logic in the same diagram. Okay. So similarly, if we were to apply the previous steps, we would say angle O2 is equals to 2y. We don't need to go through all those steps again. So what we're going to do after this is to add angle 1 with angle 2. So angle O1, with angle O2, which is equals to O1 we found to be 2x and O2 is 2y, right? So O1 and O2 is angle AOB, which is equals to, if we take 2 out as a common factor, then we have 2, which is x plus y equals to 2, and then here we found C1 to be x, we found C2 to be y. So this x plus y is then angle ACB, okay, ACB, this angle here. So we just proved that angle at the center of the circle is 2 times angle at the circumference of the circle, provided that both angles are suspended by the same arc, in our case, which is arc AB. Another one. So in this one, we are told that in the diagram, PQ is a common chord of the 2 circles. So there is PQ, it's a chord in the small circle, it's also a chord in the bigger circle. The center M of the larger circle lies on the circumference of the small circle. There is M, it's a center on the large circle, it's on the circumference on the small circle. Let's try to remember anything that we can remember with centers and circumference. Okay? First, we know a theorem that says an angle at center or at the center of the circle is twice angle at the circumference of the circle, provided that they are both suspended by the same cord. Do we have such a case here? Yes. If you look at M1 is a center in the bigger circle, and then it's suspended by PQ. R is an angle at the circumference of the bigger circle, it's also suspended by PQ. So we know a theorem that tells us then M1 is 2 times R. Angle at center is twice angle at the circumference is the reason. Okay? And then we are further given that PM and Q is a cyclic quadrilateral in the smaller circle. PM and Q is a cyclic quadrilateral in a smaller circle. What we know of cyclic quads, we can look for a bow tie, we don't see it then, but we know that an exterior angle of a cyclic quad is equals to the opposite interior angle. So if you look at the cyclic quad, we do have an exterior angle there, N2. Okay? So N2 will then be equals to P2. And this P2 is X. It's given to be X. Okay? So that's an exterior angle of a cyclic quad. Exterior angle of cyclic quad. We also know, based on the cyclic quad theorems, that opposite angles of a cyclic quad are equals to 180. Let's just put them in case if we need it later. So P2 plus N1 will be equals to 180. Also, M1 plus Q will be 180. There is a theorem that says opposite angles of a cyclic quad are supplementary. And then we were told that Qn is produced to meet R, and then point also Mn is produced to meet PR, and P2 is X. Okay, that's the given information. So let's go for the questions now. The first question in this case is that give a reason why N2 is equals to X. There's N2. Okay, while we were reading the information, we had already determined that our N2 is equals to X. Then the reason here will be exterior angle of a cyclic quad. An exterior angle of a cyclic quadrilateral is equals to the opposite co-interior angle. That is our reason. Then we are required to write down another angle equal in size to X. Give a reason. Yeah, we always give a reason. So let's check the, okay. So in the bigger circle we have radii. Okay. MP is from the center to the circumference. MQ is from the center to the circumference. That means MP and NQ are equal, making triangle MPQ an isosceles triangle. So this means that Q1 is equals to angle P2 equals to X. And then what would be the reason? Because MP is equals to NQ because they are radii. Okay? Angles equals opposite equal sides. Alright? And then we are also asked to determine the size of R in terms of X. The size of R in terms of X, I think we did find that there. R is in relation with M1. Okay? R relates with M1 because M1 is at the center, R is at the circumference, and both they are subtended by PQ. Okay, let's take this one step by step. Obviously, then we need to find M1 first. M1, we're going to say in triangle MPQ, we've determined that triangle is an isosceles triangle. So we know that M1, angle M1 plus angle P plus angle Q1 will be equals to 180. What's the reason? The famous reason, the sum of angles of a triangle. Alright, so that means M1 will be equals to 180 degrees minus P minus Q. So that was P2 minus Q, which is equals to 180 degrees minus X minus X. This is 180 minus 2X. So we found M1, which is 180 minus 2X. But remember, we are looking for R. What do we know? Do we have any relationship between R and M1? Yes. We said M1 is equals to 2 times R. We determined that when we were reading the information given. So the reason here was that angle at center is 2 times angle at circumference. Okay, so M1 we just found that it is equals to 180 minus 2x. This is 2r. Okay, I'm just going to finish this on the other side because I no longer have space. So we said 180 minus 2x is equals to 2r. So I'm going to divide both sides by 2. If 2 cancels with 2r is equals to 180 divided by 2 is 90. 2x divided by 2 is x. Therefore, angle r is equals to 90 minus x. Alright. So the last question there says that we should prove that PS is equals to SR. So here is PS and there is SR. So the lines are on the chord PR. Okay. So do notice that we have center M. So there's a line MS that is from the center of the bigger circle and it's touching a chord. Okay. So theorem 1 states that if a line is from the center of the circle and is perpendicular to a chord, then it's going to bisect that chord, meaning that it will cut it into 2 equal parts. So if we can prove that MS is perpendicular to PR, then according to that theorem, we would have proved that PS is equals to SR. Okay. Okay. So we will start by saying in triangle SRN, that's triangle SRN. What we know about that triangle, we did find from that question that N2 is equals to X, and we found from this question that R is 90 minus X. Okay, so we know that the sums of the triangles are equals to 180. So in that triangle, we can say angle S2 plus angle N2 plus angle R are equals to 180 degrees. We always have to give a reason. So our reason in this case is sum of angles of a triangle. All right. So now we're going to have S angle S2 plus N2 is equals to X, and angle R is equals to 90 minus X. All of this equals to 180 degrees. So X minus X is 0. Then we are left with angle S2 being equal 180 minus 90, which is equals to 90 degrees. That's exactly what we wanted. So we just proved that S2 here is 90 degrees.
So that means SM is perpendicular to PR since they make an angle of 90 degrees. So MS is perpendicular to SR. So we have a line MS which is from the center of the circle M, and this line happens to be perpendicular to a chord SR. So the theorem then states that if that's the case, then this line MS bisects SR. That means it cuts it into two equal parts. Therefore, PR is equals to SR. So we've proved the statement, and we need to give a reason also. So our reason will be line from center of a circle perpendicular to a chord bisects the chord.
In this one, we are told that vertices A, B, and C. Okay, so a vertex is a corner. So we have a corner A, B, C. We are told vertices A, B, C of triangle ABC are concyclic. Don't be scared of that word concyclic. What concyclic means, it means it's a point that is on the circumference. So since A is on the circumference, it's concyclic. Since B is on the circumference, it's concyclic, and C on a circumference, that means it's concyclic. All right, more information. So we are also told that EB and EC are tangent. So that's EB and EC are tangent at B and C respectively. Okay, if you remember, we do have such a theorem. There is a theorem that says if two tangents are from the same point, then they are equal. These are two tangents, both of them are from point E. So that would mean then that those two tangents are equal. That is a theorem. Because of that theorem, we know that BE is equals to, or let's name it the way they named it, EB is equals to EC, because it's two tangents that are drawn from the same point E. So that means triangle EBC is an isosceles triangle. In that case, that means angle B1 is equals to angle C3. Maybe that information will help us. We also have a tangent chord theorem that we've learned about. Okay, so we have angle B1 here that is between a tangent and the chord. So the angle that is opposite that chord BC will be equals to B1. All right. So that means what do we have also? We have that B1 is equals to angle A. That is our tangent chord theorem. We also have the second tangent. Let's see. We have an angle that is between tangent EC and chord BC. And BC is opposite angle A. So that means also C3 is equals to angle A. It's still tangent chord theorem as well. We also given that TE is parallel to AC. A is equals to T3. That's a shape of an F. A will be equals to T3, and then we know those are corresponding angles. Okay, so this is information from previous grades. So let's see. First, they want us to prove that B1 is equals to T3. We need to prove that B1 equals to T3. So what information do we have? First, we said that B1 is equals to A. We said that B1 is equals to A. And the reason there was tangent chord theorem. Okay, that's that information we drew up there. And then secondly, we also noticed that T3 is also equals to A. It's this information we just drew here because of the parallel lines, okay? So we get corresponding angles. Corresponding angles. So since B1 and T3 are both equals to A, therefore B angle B1 is equals to angle T, which is what we are asked to prove. Great. Next, we have to prove that TBEC, that's TBEC, is a cyclic quadrilateral. So we have gotten that C3 is equals to A. Remember, we got that from there, and our reason was tangent chord theorem. Okay. Also, we have that T3 is equals to A. This we proved when we were solving one, so we can just say proven. Okay, so notice then, since both C3 and T3 are equals to angle A, therefore angle C3 is equals to angle T3. Where is C3? C3 is here, T3 is there. Notice that they are in a bow tie. What does that mean? They are in the bow tie inside that cyclic, what is supposed to be proved as a cyclic quad. We have two angles suspended by BE, so that means it's two angles on the same segment being equal. So that makes this then, therefore, TBEC is a cyclic quad. Okay, what would be our reason? Angles on same segment. Alright, so we are happy with that. So we proved that this angle is equal to that angle, and we notice that it's creating a bow tie. Both of them are suspended by BE. Then that easily proves BE CT to be a cyclic quadrilateral. Alright. Next, we are asked to prove that ET bisects. Remember, bisect means dividing into two equal parts. We have to prove that ET bisects BTC. It's bisecting here. So that means what we are required to prove is that T2 is equals to T3, because bisect means two equal parts. Where should we start with this one? Okay, we had proved that T3 is equals to angle A. We proved that one. Okay, and then also we have proved that what else can we get out of this? Okay, remember we've proved that BECT is a cyclic quad, so we can then easily say T2 is equals to angle B1. Okay, why am I saying that? Notice that T2 and B1 are on the same segment. They are creating a bow tie. This is B1 and T2, and they are both suspended by CE. Okay, so we can say angles on same segment. Okay, further, we know that B1 is equals to angle A. That was proven. We have proved that already. What is this then telling us? Okay, have a look that this makes T2 and T3 equal. Then we have T2 and A equaling B1. So that means T3 is also equals to B1 in that case. Since both T2 and T3 are equals to B1, therefore angle T2 is equals to angle T3. Then we have proved that TE bisect BTC, because where it cuts, we get two equal angles. Alright, so with the fourth question, we are given that TB is a tangent. If given that TB is a tangent to the circle through BFE. So there's BFE. We have to imagine that TB is a tangent of the circle through BE. So that means in our head, we need to have this circle. Okay, that smaller circle, that's what they are saying. If it is given that TB is tangent to the circle through BFE, so that's why I created a circle on BFE. Prove that TB is equals to TC. Alright, let's start with that one. So, what do we know? Based on that alone, we know that B2 will be equals to E2. So on that small circle that we just drew them, B2 is an angle between chord BF and tangent BT. So the angle that is opposite the chord BF is then equals to B2. Therefore, angle B2 is equals to angle E2, our resin tangent chord theorem. Okay, so what else? We know that E2, angle E2 is equals to angle C2. E2 is equals to angle C2. Notice the bow tie, okay? And we had proved that BECT is a cyclic quadrilateral. Both these angles are suspended by TB and they are in the bow tie. That means we know they are on the same segment. And then the reason for this one, angles on same segment. Great. So since both B2 and C2 are equals to E2, therefore angle B2 is equals to angle C2. So B2 is equals to C2. This then makes triangle T, B, C and isosceles, making this side equals to this side. Therefore, side TB is equals to side TC. Okay, last question on this one is that we hence prove that T is a center in the circle of the circle through A, B, and C. We need to prove that T is a center of the circle through A, B, and C. Let's start. Alrighty, so we know that T2 is equals to C1. T2 equals to C1. Remember, this line is parallel to this one that was given. It's creating a Z. So these are alternating angles. We also know that T2, same angle T2, is equals to B1. T2 equals to B1. They're in a bow tie. both suspended by CE, and then we had proved that BECT is a cyclic quad. Therefore, these are angles on same segment. And then also this angle B1 is equals to angle A. Okay, angle A, that was a tangent chord theorem that we spoke about earlier. You can just say proven, or you can write tangent chord theorem. It doesn't really matter at this stage. So notice then C1, angle C1 and angle A are equals the same angles. Okay, so we can conclude that therefore angle C1 is equals to angle A. This is C1 with angle A. That's because both of them are equal the same thing. Okay. So what does that mean? It means TAC is an isosceles triangle. That means this is equals to this. It means then, therefore, side TC is equals to side TA. Okay, we just proved 3 sides that are equal and all of them come from point A. Side TB is equals to side TC equals to side TA. All of them come from point A. So then what can we conclude? We can then conclude that T is definitely a center. What's our reason? Point A, B, and C are equidistant to point T. All points A, B, and C start from point T to the circumference, and all 3 of them have the same magnitude. They are equal. So that means they are radii in that circle. So that then makes T the center.